Okay, let's go on with PVT colors. At this point, you must have the concept of PVT law, and we can call the combination of PVT factors as working condition. That is, the voltage is the temperature the CMOS gate is working at. And we can name some of the interested condition point as fast, typical, slow. For fast color, we usually have good process, high voltage, and low temperature. For slow point, we usually have bad process, low voltage, and high temperature. And in the middle is usually typical. And you can also name the working condition of this point, of that point, of this point, of that point. You can give name to this working condition as you wish. If we collected all the working condition, all the valid working condition up, we will give a line. We will give a line like that. The line denotes the slowest to the fastest condition that the chip is allowed to work at. As we have seen before, in our digital circuit, the PMOS and NMOS are always paired. So you have a line to denote the working condition of NMOS. You need the other line to denote the working condition of PMOS. It also has slow color and fast color. In this figure, this point denote the NMOS is working at slow color and the PMOS is working at slow color. This point denote the NMOS is working at fast color, and the PMOS working at slow color. This point, NMOS slow, PMOS fast. So this will give us a rectangle. Within this rectangle, these are all the valid PVT conditions, PVT working conditions the chip must work. This gives us a rectangle. The PVT conditions within this rectangle is all the conditions that our chip must work well. And the PVT conditions outside this rectangle, such as this area, is out of the working range of our chip. So your chip function can fail for this working condition. And for fast color, the transistor usually has small delay, and for slow color, the transistor must have big delay, small delay. So you can say the effect of PVT factors is just making the delay of transistor a little bigger, a little smaller, a little bigger, or a little smaller. Well, for a real case, the PVT condition shape, the shape of the PVT condition is not a rectangle. It's a polygon like that. This is because the working condition of PMOS and NMOS, they have some relationships. For example, for this point, it's impossible for NMOS to work at fast color while the PMOS works at slow color. This is usually impossible. So the shape of the PVT corner isn't a rectangle, it's a polygon. Okay, there is some load. Let's introduce load 2 first. It says for some advanced process node such as 40 nanometers and below, the cell delay may increase when temperature is low. Let me draw a curve to show that. This is the temperature. This is the cell delay, and this may be minus 14. This is 125. So the cell delay may be in this. Maybe something looks like that. Okay. And for the first load, it says, if you consider the delay of data path, there is variation on the delay of the wires. That is because the wires has capacitance and resistance. So the wires can be treated as a RC network. The resistance value and the capacitance value will change. The foundry can't make sure the capacitance and the resistance value is constant. So there is variation on the value of the RC. So when you collect cells up, there is wires. When you collect inverters up, there is wires. In this figure, we just considered the variation of the NMOS and PMOS. If you also consider the variation of wires, the shape of the working corner needs to change. From 2-dimensional to 3-dimensional. For example, you may draw something like that. This is the NMOS, this is the PMOS, and this should be the wire. The wire delay variation. So you may say something, draw something like a cubic. Okay, okay, it's hard to draw. It's hard to draw. You can try it by yourself. Okay. Something like that. Yes. Okay. So this may be the working condition for a chip. Or the valid working condition for a chip. Okay. That's all for this chapter. There is some small questions for you. Can you draw a diagram of an inverter using NMOS and PMOS symbols? I think this should be easy. And please draw the output response curve of the inverter and mark the rising and falling transition time, the rising and falling delay time in the figure. And last, please explain how PVT factors will affect the delay of a CMOS gate. I think this question is a lot harder. And last, I want to give you a more tricky question. As we have said before, the transition time of a signal must be positive. If we treat this as a RC circuit, the transition of a point must be positive. And the question is, where this delay of a cell can be negative. For example, the delay of the inverter can be a negative value. For example, minus 0.1 nanosecond. Can the delay of inverter be negative value? I will give you some hint. First, you have to refer to the defining of the delay. And you have to think about the threshold voltage for PMOS and NMOS. Okay, that's all. Thank you.